my bookmark. Oh, there it is. Interesting. Probably zoom in a little bit further. So this problem is asking about R double quote A. R double quote A is equal to the range of R pipe A. And the range operator let's see here. The range operator is going to reference, let's see, the existence of an ordered pair where the element that's in the range, the range of A is equal to the set containing its elements Y such that there exists an X such that the ordered pair XY is an element of A. Why is that interesting or alternatively a problem? So if I say, so for all n is an element of the range of A is interderivable with the expression there exists in M. So we need P. P is an element of the range of A is interderivable with the expression there exists in such that the ordered pair in P is an element of R. Element of A, rather. And let's make that a B. Okay, and why is that interesting? Well, I think it makes us write out more of the definition when I say R double quote C is equal to the range of R pipe C. Okay, then I am saying for all, run out of letters, for all Q, maybe we should just be resetting our letters. It's interesting how many sort of practices we pick up. Like, on the next such example, we're going to be recycling our letters and trusting ourselves not to get confused. Why? Because otherwise we run out of letters. But you only realize that running out of letters is a problem, or you might only realize running out of letters is a problem when you're in the midst of practice. Okay, for all Q, Q is an element of the range of R pipe C is interderivable with the expression that there exists an R such that the ordered pair RQ is an element of R pipe C. Okay. So now I say R pipe C, what does that mean? Well, we just wrote out the definition, so if we need to go back to look at it. Okay. Here we go. R pipe C is equal to R intersection A by the range of R, so rather C by the range of R. Okay. So the ordered pair RQ is an element of R pipe C. is interderivable with the expression R pipe. Nope. What? Ordered pair RQ is an element of R, and ordered pair RQ is an element of, nope, rather, R is an element of C, and Q is an element of the range of R. Yeah, we did this fine on the first. we did this just fine up here, and then maybe the process got more complicated. The process of sequentially breaking down this expression. Let me see here. Yeah, let's start over and keep consistent. Or use my typical okay, so starting back at the beginning, this is saying for all, yeah, we'll recycle letters now. Well, we won't need to recycle letters now, presumably, because we're starting from the beginning and doing a single chain. Alright, so for all P is an element of R double quote A. Okay. We can do R converse, since that's actually part A. Alright, R double quote. Yeah, actually, let's make the definition without the converse, and then we can just sub back in. Okay. So, for all P is an element of R double quote A, is interderivable with the expression that there exists an N such that the ordered pair in P is an element of R pipe A. Okay. Which is interderivable with the expression. There exists an N such that the ordered pair in P, so our pipe A is, right, there exists an N such that the ordered pair in P is an element of R and the ordered pair in P is an element of A by the range of R. expression. There exists an n such that the ordered pair in P is an element of R. And n is an element of A. And there exists an M such that the ordered pair Mn is an element of R. Okay. What? Rather, MP. Now, seemingly we should be able to... Yeah, okay, the work is being done by the quantifiers. We already had this, but we hesitated because... Let's see if and only if... There exists an n such that the ordered pair in P is an element of R, and n is an element of A. And we hesitated because I think here. Right, how do we get out the fact that we're interested in P and the work is being done by the quantifier? So if we want to highlight that fact, we could say, well, we could do the double derivation and say all of this obtains. So here we could do red, orange, and a little bit of organization here. So there's this n. I'm going to close out that quantifier. Now what we are saying is that for all P is an element of R double quote A is interderivable with the expression there exists an n such that the ordered pair in P is an element of R and n is an element of A. Okay. And now we need to specify R. What are R's characteristics? We're saying that R is the numerical relationship, R is the numerical relation such that for all D is an element of R if and only if it's interderivable with the expression there exists an R and there exists an S such that D is equal to the ordered pair RS and 2r minus s is equal to -1, which we have not done anything with arithmetic outside of the preceding exercise. I'm motivated to do this. Okay. And we could say that this is equivalent to saying that for all ordered pairs of the form Rs, the ordered pair Rs is an element of R is interderivable with the expression that 2R minus S is equal to -1. Okay. And now we want to plug that into... Yeah, I'm not sure I want to take that substitution. That might be better colored. This. Okay. Now what? Well, okay, but we have this, so we're saying the ordered pair in P. Okay, so let's do this again and say for all P, P is an element of R double quote A. We're reducing the number of brackets somewhat. Interderivable with the expression there exists an N such that, yeah, we'd be using this definition, so we directly state such that 2R minus S, well, here we would just do NP, right? Let me think here. Yeah, okay, because we're starting from here, from this statement, this ordered pair expression, or ordered pair term NP, so 2N minus P is equal to -1. And N is an element of A. Okay. Now, what set is R double quote A? Okay, well, A, we'll need to give ourselves a refresher here. A is equal to the integers, so A is equal to the set containing its elements (((), -2, -1, 0, 1, 2, ... Okay, and then we have Well, if I give myself sample elements, I would say, well, corresponding elements, sure. R double quote A is equal to the set containing its elements dot dot dot, so -2 times 2 is -4 minus P, so I add -4 over here, I get +3, and I get -3. After multiplying by -1. Okay, I plug in -1, I get -2, I add over here, I get +1, and then I get -1. Plug in 0, I get +1. Plug in 1, I get -3, I get +3. Okay, plug in 2, I get 4. I subtract, I get -5, and then I get 5. Dot, dot, dot. Okay. And it turns out that that is the the odd integers, rather. Okay. And now I have this convenient formula. Alright, so this was exercise 25B. Alright, and now exercise 25A can recycle this by saying for all P is an element of R converse, double quote A, is interderivable with the expression that there exists an N such that the ordered pair in P is an element of R converse, and N is an element of R. N is an element of A, rather. Yeah. And this is a direct typographical substitution. If we had instead replaced R with Q, or whatever, then we would be typographically replacing Q with R converse instead of typographically replacing Q with R. And we'll do the same thing for part C. Okay, so alright, and this is interderivable with the expression there exists an N such that the ordered pair Pn is an element of R, and N is an element of A, okay, which is in turn interderivable with the expression. There exists an N such that and now we need to replace the letters, so this is going to be, and notably N is bound by N being an element of A, which sort of highlights the idea of binding here, I think. Alright, so this is going to be yeah, just right here, so 2P minus N is equal to -1. Okay. And N is an element of A, so once again, if we give ourselves A is equal to the set containing its elements -2, -1, 0, 1, and 2. Then we have that R converse double quote A is equal to the set containing its elements. So negative 2 is going in for n, so this will be 2p plus 2 is equal to negative 1, 2p is equal to negative 3. Yeah, it'll be negative 3 hells. Alright, negative 1. We have negative 2, so it'll be negative 1. Plug in 0, it'll be negative 1 health. Plug in 1, we get 0. Plug in 2, we get 1 health. Dot, dot, dot. Okay. Probably I could put those side by side, though it's illustrative to sure. Could have done this as 2 halves to be more informative, maybe. Okay. And now part C. R/R double quote A. Alright, let's see. So we once again have a typographical replacement conveniently. For all P. For all P, P is an element of R/R converse. Nope, R/R. R/R double quote A. If and only if there is interderivable with the expression there exists an n such that the ordered pair in P is an element of R/R, and n is an element of A. Okay, had to dodge that. Embarrassing mismanagement of the notebook. Alright, and what is the slash relationship? There exists a Q such that. Yep. Alright, if and only interderivable with the expression. There exists an n and there exists a q such that the ordered pair in Q is an element of R, and the ordered pair QP is an element of R. Yeah, this is fine. And n is an element of A. Okay, and now this is interderivable with the expression. No need to labor in unassisted confusion. Though this is a little bit more confusing. What makes this a little bit more confusing? So we don't have a source for our Q elements. And for that matter, we don't have a source for our P elements. So I am thinking. What do I mean? Well, this and in as an element of A has had a natural function, has had a natural purpose up to this point of informing our expression 2A minus B is equal to -1. But now we don't have, where n was S in this example, now we don't have, no, actually, n was R in this example, not that it matters. So this is completely unmoored from the set A. This has elements from the set A. It's like this is a leak in the definition or something. It's like we have a memory leak, as it were. I don't know what memory leaks are. I don't have to work with memory. I run our code in Lisp. Requires no understanding of memory. Right, well, so the idea is that these seemingly could be anything. These could be any combinations of numbers. The only constraint we have, the only typing we have is that n is an integer, or A is the set of integers. We don't have any typing on this set. I mean, I guess we inherit typing of numbers as opposed to ordered pairs or whatever from the fact that we have an arithmetic expression informing the contents of R. But we don't inherit integers. Okay, so I guess we would use abstraction notation here where there's too much hesitation. So my bookmark keeps. So r/r double quote A is equal to the set containing as elements P that are elements of the reals such that there exists well, it would just be the reals, yeah. Because we can always target -1. We can always set up this, we can target any real using this equation to r minus s equals -1. So it's a defective definition if the point was to restrict. Okay, so I think. Now, last exercise for the section, prove that r double quote the empty set is equal to the empty set. Okay. Exercise. What is this? 29. Alright, so double quote. R double quote the empty set is equal to the range of R pipe the empty set. So for all P, we could do that again. For all P, P is an element of R double quote the empty set is interderivable with the expression there exists an N such that the ordered pair in P is an element of R pipe the empty set. Okay, which is interderivable with the expression. Let's see, R pipe A. There exists an N such that the ordered pair NP is an element of R. ordered pair in P is an element of a empty set by the range of R. Okay. Which is interderivable with the expression there exists an in such that the ordered pair in P is an element of R, and in is an element of the empty set, and P is an element of the range of R. And we need to go no further. This is a contradiction. In is not an element of the empty set, and consequently the entire expression is a contradiction. Okay. And now a little bit of Vermilion reasoning here. Constructivist reasoning. If this is a contradiction, its negation must be true somehow. That's reasonable. Alright, so not. There exists an in such that actually, I'm not sure how to finish this proof. Let's see here. I mean, this is the critical juncture, but what do you do after this? For all P is an element of... I don't know. The point would be that this is... like a cascading chain reaction up these interderivability assertions. We know that P is an element of R double quote the empty set is false. Okay, if and only if not P is an element of R double quote the empty set is true. Okay, hence for all P not P is an element of R double quote the empty set, which is defined to be equivalent to stating that R double quote the empty set is equal to the empty set. Alright. Okay. Those were the exercises. The next section is ordering relations. take a break prior to that. I'll be right back. Alright, sit right back, chat, and I'll tell us a story about relations. Ordering relations. Section 3.2. Relations which order a set of objects occur in all domains of mathematics and in many branches of the empirical sciences. There is almost an endless number of interesting theorems about various ordering relations and their properties. Here we shall consider only certain of the more useful ones. A large number of additional theorems are included among the exercises. We begin with the fundamental properties of reflexivity, symmetry, transitivity, and the like, in terms of which we define various kinds of orderings. Because these notions are so familiar, illustrative examples are given only sparingly. Okay. Regarding generality of definition, the situation is the same as in the last section. The definitions hold for arbitrary sets, not for just relations. However, in order to increase the immediate intuitive content of the theorems in this section, we shall systematically use letters R, S, and T as set variables in those contexts in which the ideas being dealt with naturally refer to relations. But it should not be strictly understood that use of the variables R, S, and T does not entail any formal restriction on the definitions and theorems. For instance, we define the property of transitivity for arbitrary sets R, not merely for relations. Though it's not clear to me how reflexivity, transitivity, etc. apply to non-relations. It seems like these definitions require, well, they explicitly mention order pairs. Well, anyway. Also, without introducing a numbered definition, we henceforth use the familiar notation x, y are elements of A for x is an element of A and y is an element of A, and x, y, z are elements of A for x is an element of A and y is an element of A and z is an element of A, etc. We begin with 8 basic definitions. Those are the definitions of reflexivity, irreflexivity, symmetry, asymmetry, antisymmetry, transitivity, connectedness, and strong connectedness, which we will use as required, or reference as required. In order to relate the above 8 properties to the operations introduced in the previous section, it is more elegant to consider the corresponding one-place properties. That is, to deal with relations which are reflexive rather than reflexive in some set A, etc. The general definitions just given are useful later. For brevity, we define the 8 one-place properties in one fell swoop. The definitions are obvious, we simply take A to be the field of the relation. Alright, so for each of these definitions, we have a kind of meta definition. I will write down the meta definition. R is one of these definitions is equivalent to saying that R is in the field of R. In formulating the desired theorems, we need the notion of the identity of relation on a set. It is clear from theorem It is clear from Theorem 50 of Chapter 2 that the set containing its elements x such that x is equal to the empty set by definition, because we don't have a universal set. So it is clear from this theorem that we cannot define an appropriate general identity relation. But what we can do is define for each set A the identity relation identity of A on A. Thus, the symbol identity is not an individual constant designating the identity relation, but a unary operation symbol. I don't really know what that means. We'll try to find out as we go along, I guess. Alright, so the identity of A is equal to the set containing as elements ordered pairs of the form P such that P is an element of A. Okay. So for all D is an element of the identity of A. It's interderivable with the expression that there exists a P such that D is equal to the ordered pair PP, and P is an element of A. Okay. And now we have our first theorem. Theorem 42. The ordered pair X, the ordered pair SS, the ordered pair T. T is an element of A, the identity of A, rather. Is interderivable with the expression. T is an element of A. Okay. Well, going by the definition, we say yeah, well, this insistence on laying out definitions like this leaves us these terms like D is equal to the ordered pair PP. And that has proven to be a problem for some of our proofs. So it might be that this is excessive. Though, if possible, I would like to maintain this because it makes things easier to consider, I think. Okay, let's see. So, This is the definition we just used. And the point is that, well, we've given ourselves the ability to drop and introduce this term without stepping down. That proved critical in at the end of one of the earlier exercises, where we had this term, a term like this in the sense that, well, like what we just said, where we can drop or add this term without stepping down a biconditional or an interderivability assertion. If we were to distribute through in that exercise, this was a term, and if we distributed through to it, we would have this additional awkward term that we couldn't get rid of, and our proof fell apart. So our sleight of hand was that we could eliminate this without stepping down the interderivability assertion, perform the distribution, and then reintroduce it, which is effectively saying, I don't know, that this is pure record keeping. Though then one wonders, has this never proven critical in any of our proofs? Well, though again, if we can introduce a term like this whenever we want, then even if a term like this proved critical, we could always introduce it. So, yeah. I don't know, hand wringing. I'm not sure that I understand this proof. So this is saying the ordered pair XX is equal to the set containing X and the set containing XX, which is equal to the set containing its elements X. Curiously. Quirk of the definition for an ordered pair. Quirk. So it is clear that the identity of A is a subset of the power set of the power set of A. True enough, if we start with A as containing merely X, and then we take the power set, we get the set containing X and the empty set, and then we take the power set again, we get, I don't know anything about the power set. Well, at any rate, we get this element back. If nothing else, power set introduces another set wrapping around every element, in addition to everything else it produces. Okay, so it is clear that the identity of A is a subset of the power set of the power set of A. It seems like the power set was introduced to make various proofs possible. Has been my limited observation about the power set. That's the only way it's been used in this book up to this point, is proving theorems. Though you might say that's the only way anything has been used in this book. But anyway, by virtue of the axiom schema of separation and the definition of abstraction, we may use one to obtain the theorem. Let's see. Yeah, I don't know what that proof is telling me. I don't doubt the correctness of this proof. Can we simply use our definition? How would we do that? Let's see. Yeah, well, I mean, I think we could just get away with doing that. I don't know. I'm gonna. Well, yeah, I mean, if it's just, this is true of all D's, so if I say the ordered pair T is an element of the identity of A, if and only is interderivable with the expression T is an element of A. By reflexivity. And I think the proof assistant would take that. Alright, so I'll leave that alone. In this and subsequent proofs in which the axiom schema of separation, in this and subsequent proofs which use the axiom schema of separation to prove the existence of some set, we restrict ourselves to consideration of two crucial steps. Deciding what set known to exist has the desired set as a subset, and then showing that satisfaction of the appropriate condition phi in the axiom, here phi is X is an element of A, implies membership in the larger set. That is a clarifying remark that would have been helpful in prior to all of the earlier proofs that used the axiom schema of separation. So the axiom schema of separation, if we go back all the way back here, there exists a B such that for all X, X is an element of B if and only if X is an element of A and phi of X. Okay. And the point here is that we want to show, so X is an element of A. It seems like that could use some quantification. But so what the author is saying is that we prove first that there is some A, some set of which the desired set is a subset. So let's reread this. In this and subsequent proofs which use the axiom schema of separation. And so that's the point of saying that the identity of A is a subset of the power set of the power set of A. That gives us our A. It gives us our set where the identity of A is discernibly or knowably known to be a subset of that other set. Okay. In this and subsequent proofs which use the axiom schema of separation to prove the existence of some set, we restrict ourselves to consideration of two crucial steps. Deciding what set known to exist. So it's saying, so the point of saying known to exist here is that we don't want to be talking about an empty set. So we have to prove that there's some set that we can derive from earlier proofs, or some set that we can derive from earlier theorems, axioms, etc., that we know to exist. So it's like we're expanding the collection of known sets, and then we have to be able to identify the set we're looking for as a subset of one of those known sets. Okay. And then showing that satisfaction of the appropriate condition phi in the axiom implies membership in the larger set. So in this case, X is an element of A is our phi. Okay, then we know that the set containing X is an element of the power set of A, and we know that that set exists, so we know that I'm going to leave it at that. Okay, let's see. It is perhaps clarifying to remark that the formal proof does not require the inference that the identity of A is a subset of the power set of A, although this easily follows. So it doesn't have to be the power set of A, but it would have to be some set that we can prove exists, and we know that this set exists, so it's good enough. But the search for a set that has the identity of A as a subset is an essential strategic consideration in finding a valid proof. Okay. We state without proof 3 simple theorems concerning identity relations. Okay, theorem 43. The domain of the identity of A is equal to A. Okay. It just struck me that I'm motivated to pick up colored pencils and deposit them back into their trays when there are enough on the table that I can't find the one I'm looking for immediately. Okay, so it's like triggering garbage collection. I would say if I knew anything about memory, which I don't. Alright, let's see. Oh, and then... I think we will start with A. So for all P is an element of A is interderivable with the expression the ordered pair PP is an element of the identity of A. Alright, so then we can step down. I guess we'll have to do this in both directions. We can step down this expression to saying there exists a Q such that the ordered pair PQ is an element of the identity of A, which is interderivable with the expression that P is an element of the domain of the identity of A. Okay. So that's in the right to left direction. Let's do the left to right direction. Okay. For all D, no, this would be, we'll do R. For all R, R is an element of the domain of the identity of A. It's interderivable with the expression that there exists an S such that the ordered pair RS is an element of the identity of A. Not quite sure what to make of this here. Uh, let's see. So maybe we could step this down and say. Probably should have new lined that. Yeah. There exists a D such that D is an element of the identity of A, which is interderivable with the expression D is equal to the ordered pair. There exists an S, there exists a T, there exists a U, such that D is equal to the ordered pair U, and U is an element of A. But that doesn't work because that gets us that U is an element of A. Yeah, well, I mean, the problem arises from not being able to pattern match on this definition, or on this theorem. because we don't know which of these two t's is this t that is an element of A. And I mean, obviously, in context, or if we give ourselves semantics for a moment, R is equal to S. I mean, there might be some obscure binding point that makes this relevant in an upcoming proof. Like, the related point would be that I might be able to say R is an element of A and S is an element of A. But how do I get... we could say... I'll do a little bit of sort of scratch work below as a continuation. So t is equal to t. P if and only if p and t is equal to t. If and only if p. And that is because t is equal to t we take to be a tautology. Though that raises the question, what is this operator equality? This has a definition in terms of set equality. We have the set-based definition of equality, which says that A equals B if and only if, or is defined to be equivalent to if A equals B if and only if for all P and for all P if P is an element of A, then A equals B if and only if for all P if P is an element of A, then P is an element of B, and if P is an element of B, then P is an element of A. Though, critically, the book doesn't give us that definition of equality, we give that to ourselves. Okay, so it's not clear what T is equal to T means here in the general case. There's effectively an assertion there that these are sets, which we might not want to carry around with us with our definition of equality. A question that's similarly raised back here with this exercise. Like, this is an undefined term. It's kind of a meaningless term, which is why I underlined it in goldenrod. We can't read it because this arithmetic expression is meaningless in our axiomatic set theory. We just know what to do with it somehow. Okay, but what is the point of this? So if I say this is a tautology, if I say for all P, P equals P, I can and on a tautology wherever I want. Similarly, I can or on a contradiction and then remove that contradiction I mean, I can OR on anything I want, but if I OR on a contradiction, I can also OR remove. Okay. Now, so the idea would be... This seems a little bit tricky. A little bit sleight of hand. If I say T is an element of A is interderivable with the expression... I don't want to use T there. I'll use S. S is an element of A if and only if the ordered pair SS is an element of the identity of A, which is also interderivable with the expression. The ordered pair SS is an element of the identity of A, and S is equal to S. Now the question is, do I want to give myself pattern matching off of that? Yeah, interesting. That could be a use for our other orange. Alright, so do I want to give myself pattern matching here? Because then the idea would be that if I say there exists an S such that the ordered pair RS is an element of the identity of A, is interderivable with the expression there exists an S such that the ordered pair RS is an element of A and R is equal to S. Okay, and I justify this by pattern matching, as mentioned. I'm not sure that qualifies as pattern matching. I'd have to think about it a little bit more. There exists an S such that the ordered pair RS is an element of A and R is equal to S. Okay, in which case this would be interderivable with the expression the ordered pair R is an element of... Oh, that should be the identity of A, rather. I feel like I do my best calligraphy on letters I have to erase. And then replace it with bad calligraphy. The ordered pair RR is an element of the identity of A. Though, interestingly, that also steps down this quantification without stepping down our assertion. Now, for the purposes of this proof, we could actually step down because we're doing from both directions. So even if we did have to step down this assertion of interderivability to forward derivability, that wouldn't disrupt this proof, but it might disrupt other proofs. Yeah, well, we only have to settle this once, I guess. And then on, it's just automatic. I guess this would be our justification. Okay, sure. The identity of A slash the identity of A is equal to the identity of A. Okay, can we finish this on the same page? No idea. We'll try. It's theorem 44. Alright. Fine. Why is my hand betraying me? Theorem 44. Alright, the identity of A. Slash the identity of A is equal to the identity of A. Okay. So what is that slash operator again? That's the pipe operator. That's the, there exists a something such that, right? Yep. Alright. For all D, D is an element of the identity of A slash the identity of A. Is interderivable with the expression. No, yeah. Interderivable with the expression. There exists a P and there exists a Q such that D is equal to the ordered pair PQ, and there exists an R such that the ordered pair PR is an element of the identity of A, and the ordered pair RQ is an element of the identity of A. And interestingly, what we were fretting about in the last what we were fretting about during these notes immediately becomes relevant. So we take this to be interderivable with the expression D is equal to the ordered pair PQ, and there exists an R such that the ordered pair PR is an element of the identity of A, and P equals R, and the ordered pair RQ is an element of the identity of A, and R equals Q. Okay. So we get some transitivity here. P is equal to R is equal to Q, so P is equal to Q. D is equal to the order pair PP, and the ordered pair PP is an element of the identity of A, and the ordered pair PP is an element of the identity of A. And here we can and remove without stepping down. If and only if D is equal to the order pair PP, and the order pair PP is an element of the identity of A, which is interderivable with the expression that D is an element of the identity of A. And that's the kind of satisfying step that maintaining this convention gives us. Not strictly necessary, but deeply satisfying. Right. I guess what we'll do is next theorem. Theorem 45. R is a relation is interderivable with the expression the identity of the domain of R / R is equal to R. Okay. Well, that's an interesting one. So, R is a relation, is defined to be equivalent to the expression for all D, if D is an element of R, if and only if there exists a P and there exists a Q, such that D is equal to the ordered pair PQ. Okay. And this is the logical operator, not the, I don't know, metalogical operator. It's not an assertion about derivability. So this is interderivable with the expression that if D is an element of R, then there exists a P and there exists a Q such that D equals the ordered pair PQ. And is this not biconditional? It doesn't really make sense if it doesn't ring in my ear if it is biconditional, so let's go back. No, it is not biconditional. So rather, let's R is a relation the expression that for all D, if D is an element of R, then there exists a P and there exists a Q such that D is equal to the ordered pair PQ. Okay. Alrighty, then what do we want to do with that? That is entirely unclear. Okay, we will do, well, we can break this down a little bit further. Interderivable with the expression there exists a P and there exists a Q such that D is equal to the ordered pair PQ, or not. D is an element of R. Alright, that will be our left-hand side. Now what about the right-hand side? I'm sure this will be horrible. Let's find out. I'm confident this will be horrible. Let's find out. Alright, so, So this is expecting ordered pairs, because if we take the domain of R, well, then that anticipates R is ordered pairs. Well, and that's reasonable because R is a relation. Then, let me see. then if we take the identity, so the domain is going to give us one element out of the ordered pair, and then the identity is going to reflex the, I don't know if we can use reflex as a verb like that, but whatever, it's going to reflex the element. Okay, so for all E, E is an element of the identity of the domain of R if and only if E is an element of R. Okay. Which is interderivable with the expression if E is an element of the identity of the domain of R, then E is an element of R, and if E is an element of R, then E is an element of the identity of the domain of R. Okay, let's do a lemma here. Under what conditions? Under what condition is? Under what condition is E an element of the identity of the domain of R? For all F is an element of the identity of the domain of R if and only if there exists a P such that F is equal to the ordered pair PP and there exists a Q such that the ordered pair PQ is an element of R. Is that right? Let's see. E and P is an element of the domain of R. Okay, yep. All right. I'm not sure what to do with that. Well, we close the lemma and then we plug it in. That's what we do with that. All right, let's do that. E is, we'll just go ahead and do the negation here. Not E, not there exists a P, not there exists an S, sure. such that E is equal to the ordered pair SS, or E is, oh no, and there exists a T such that the ordered pair ST is an element of R. Okay. Or E is an element of R. And there exists a U such that E is equal to the ordered pair U, and there exists a V such that the ordered pair UV is an element of R, or not. E is an element of R. Is it time to do some horrible logic? Yes, we should have had that shifted over to adhere to our formatting rules. Let's see. Horrible logic time. Actually, let's do another step where we distribute this through. So, interderivable with the expression for all S not E is equal to the ordered pair SS, or for all T not the ordered pair ST is an element of R, or E is an element of R, and there exists a U such that E is equal to the ordered pair UU, or there exists, no, and there exists a V such that the ordered pair UV is an element of R, or not E is an element of R. Okay. So the easier way to distribute this is, there's not an easier way, I think. Let me see. Seems like there should be an easier way to distribute this because this is or-wise associative. I'm afraid that doesn't end up doing anything for us. Well, you know, there's nothing for it except to do it. Yeah. Let me see. Well, so if we make this the P, this Q, and this R, then we would have P and Q or P and R. And the idea is that we would distribute this term through P and R. So we would get... No, that gives us one contradiction. That doesn't really save us anything. Wait, is there a way that we could do... Let's see here. Trying to see if there's a tactic where we could step down easily. So we have this OR expression. Okay, so the idea is that we could AND off this term, this top line, and then we would have not E as an element of R, or there exists C, and then we also AND down this term. And then we would have there exists a U and there exists a V such that the order pair UV is an element of R, or not E is an element of R, which gives us this term. So we can go back in that direction cheaply. And then the follow-up idea would be that we might be able to construct each of these terms as a contradiction by ORing on a contradiction. I'm not sure that makes sense. Let me see here. So to go back to the right-hand side, we AND down the top line because this is and we AND off this term, and then we have verbatim pattern matching. And in order to go in the other direction, we would try to construct contradictions so that we could get an AND on, since we ANDed on, or no, we would try to construct a tautology. Okay, but yeah, I don't know how to do that at the moment, so we're not going to do that. All right. Very well, then it comes down to distribution, and what is the distribution that we want to take? Yeah, I'm having trouble thinking about this. Well, we're going to get a bunch of contradictions here because we're saying we have these two terms that are going to get combined with these terms in turn. So this term combined with this term is a contradiction. This term combined with this term is also a contradiction. So the question is, how do we get those terms together as quickly as possible so that we can avoid calculation? And that also is not occurring to me. Let's see. I think we're supposed to make this the p term. What little sense of this I have is that we make this the p term. Okay, and then this will be the q, r, and s term. These will be the q, r, and s terms. Okay. And I guess that's actually, yeah, I don't know how to handle the quantifiers here either. This is getting awkward. Okay, so we will have for all s, not s. I guess, I mean, we could just slap a quantifier out front. For all s, not e is equal to the ordered pair s, and E is equal to the ordered pair u, and there exists a v such that okay, for all s, not there exists, not e is equal to the ordered pair s, and then there exists a u such that e is equal to the ordered pair eu. There exists a v such that the ordered pair uv is an element of R, or not e is an element of R. Okay. For all s and for all t. I'm not sure that this is a valid way of doing the quantifiers here, but we're gonna look at it. For all s and for all t, not the ordered pair st is an element of R, and I'll just do blue Maybe that will not complicate matters. Okay, we probably didn't need to color both of these, but whatever. And then black. E is an element of R, and alright, and now the horrible bit. Well, actually, is this horrible? Because as we noted, when we distribute this term, this is going to make a contradiction. So similarly, for all S and for all T not, the ordered pair ST is an element of R, I take to be a contradiction with the assertion that there exists a U and there exists a V such that the ordered pair UV is an element of R. So this will be a contradiction, and then E is an element of R will be a contradiction with not E is an element of R. Okay, which leaves us with the remaining terms. Interderivable with the expression. For all S not E is equal to the ordered pair S, S, and not E is an element of R. Uh-oh. Let's see. So these would all be ORed. P and Q or R or S, then P and Q or P and R or P and S. Okay, so or and or. Right, then or for all S and for all T, not the ordered pair ST is an element of R, or not E is an element of R. Yeah, well, this ends up, I think, being precisely what I was saying about we can just OR these two terms on. From up here. Alright. E is an element of R, and yeah, but that observation only goes in one direction. I think there exists a U and there exists a V. that should be an and. Okay, so E is equal to the ordered pair U, and the ordered pair UV is an element of R. Okay, which is now all and Y's associative. Really? That's the solution here? So we can step this down to the right, and reducing E as an element of R, not the ordered pair ST as an element of R, and not E equals the ordered pair SS. Then we have not E as an element of R, or not E as an element of R, or E equals the ordered pair UU, and the ordered pair UV is an element of R. Okay. That doesn't quite get us where we want to go, because we can't do that in the other direction. What do I mean? This ended up being horrible. Starting from here, we can't actually get the O-ring that we want. Let me think here. Well, because we'd have to be able to arrive back at this expression. Okay, but actually, yeah, I'm unsure. This has gotten out of hand. I mean, we can go ahead and claim and then rewrite this out to see if we want to reuse it. So I need to do some garbage collection. So we're saying we and reduce these two terms. Yeah, and then we and reduce these two terms. Yeah. Okay. the absurdity. Let's do a little bit of garbage collection. Alright, so this is from the right-hand side. Okay. Trying to figure out what horrible logic trick I'm supposed to pull off to make to go in the rightward direction. So again, these two terms are associative or-wise. So this term we might be able to delete. We might feel free to delete without stepping down. Or introduce freely. Right, so again, the point of the or, of these two or terms, we can or them on freely. So if we could derive any of these from the left-hand side, then we can or on the others and get a forward derivation from the original expression, from the left-hand expression. Then the critical difficulty is that well, our starting base from which to derive any of these terms doesn't seem to allow the derivation of any of these terms. Oh. Yeah, but then what do we do with this term? So this, there's an implicit for all E way back here, the quantified for all E. So this term and reduces by itself. This term and reduces by itself. We say for all E, not E is nominative R, and not the ordered pair ST is nominative R. That's a trivial expression, trivially derived. So if I start with for all D, not D is an element of R, then I can get not D is an element of R and not the ordered pair ST is an element of R, and then I or introduce these two terms, two expressions above and below. That is horrible. And then what? Well, then we have this hanger-on or expression. There exists a P and there exists a Q such that D is equal to the ordered pair PQ. And it's less clear how I'm going to get that. Or what I'm going to do with that expression. Well, this might be where we have to remove this, reliance on this term that says D is equal to... Well, really, then this is the point where we start introducing this term. Instead of saying for all D, we say for... Yeah, but then that doesn't make any sense. This is merely the definition of a relation. I don't want to say for all ordered pairs of the form PQ such that PQ is an element of R, PQ is an element of R, or something like that. I guess we'll make that note. We're about to wind down for the day. Okay, so if I take... We might need to redo this one. I say that often and then I don't so often redo them. There exists a P and there exists a Q such that D is equal to the ordered pair PQ. That should have been parens and this should have been bracketed, but whatever. Or not D is an element of R. Okay, so now we want a bit of a lemma. No, we need the quantification. For all D, not D is an element of R, we take to be interderivable with the expression not D is an element of R and not the ordered pair ST. For all S and for all T. Not the ordered pair ST is an element of R. Okay, I believe it. So now I have interderivable with the expression there exists a P I might have a horrible idea that gets us there. Let's see. Okay, let's whatever, I'll just write it out. Okay. So this would be forward derivable. Which is fine because we already forward derived in the other direction. Step back or I'm gonna get crammed in here. Or it should be D, presumably. Okay. If I distributed this term through here, we would get No, that wouldn't be a tautology. Oh yeah, it would. Because we could extract the negation. We'd say there exists an S such that D is equal to the ordered pair SS. Wrong one. Not there exists an S, there exists a T such that the ordered pair ST is an element of R. Oh, that's not even the same expression. So we almost have it. Oh wait, hold on. Yeah, it would be this term. Yeah, but this requires the two elements to be equal to each other, and they're not equal to each other here. Yeah. I mean, we might be able to... We might be able to pull in disjunction elimination. I don't know what we would do with that. The idea would be to say that it doesn't matter which way this statement goes, whether it's true or false, it doesn't change the remainder of the expression. Huh. Yeah, I don't know. We'll come back with fresh eyes. Comparatively fresh eyes. Tomorrow. For now, I am calling it. Have a good one. Anybody in chat? Oh, I closed